Much better. Yeah. Okay, hello everyone, and welcome back to verification. We are already past the part on semantics, so we're only going to talk about verification from now on. And I see that because this is not going to be included in the exam, far fewer people showed up. Okay. But I hope it's going to be interesting. So let's pick up where we left off in the previous session. So we talked about the problem of halting or termination and showed that the problem is undecidable. Then we reformulated it and showed that a program terminates basically if and only if it has a ranking function. And this gave us a way of being able to look into the special cases of the problem. So we can look into linear ranking functions now. And basically what we did in the previous session was that we said, okay, let's assume that everything is linear. Let's assume that our programs are linear. So the conditions in our while loops and also the if conditions are linear and our assignments are linear. We also assume that we are given invariants, and we assume that those invariants are linear inequalities. And finally, what we want to do is that we want to synthesize a ranking function f. And we are again assuming that the ranking function is also linear. So we set up this kind of template for the ranking function. So at line 1 of our program, the ranking function is C0 times the value of x plus C1, and so on for the other lines. I basically use these two different notations interchangeably. So I either write f of Lx or fl of x. These are both the same thing. And basically our goal is to synthesize values for the CIs and also for that other decrease factor that we had, which we called epsilon, such that this function f becomes a ranking function and proves termination for our program. So in the previous session, I talked a little bit about Farkas lemma, and now I'm going to go into more details about it. So Farkas lemma is the mathematical tool that we use for synthesizing these ranking functions, basically for finding values for the CIs. So let's see exactly what Farkas lemma is. So let's say that we have a set of linear inequalities, and we call this set psi. And let's say that our linear inequalities are over a set V of variables. So in our use case, V would be the program variables. And V, let's say, consists of finitely many variables, which we call V1 to Vr. So our system or our set psi is basically a bunch of linear inequalities. And I can write them in this format, right? So it's A10 plus A11 V1, so on to A1 RVR greater than or equal to 0. And then I have n different inequalities. So this is the second inequality and so on until I have the nth inequality. So I have a set of n inequalities, and let's say that I have some other inequality which I call phi, and this is B0 plus B1 V1, so on to BR VR. Okay, so what we are interested in is figuring out whether, assuming these inequalities, we can conclude that this inequality also holds. So basically what we are interested in is to see if for every value of the variables, having the n initial inequalities leads to also having the final inequality phi. Okay, and now Farkas lemma, what it does is that it tells us this whole thing holds, so we can deduce phi from psi, if and only if we can write phi as a non-negative combination of the inequalities in psi and also this trivial inequality, 1 greater than or equal to 0. Okay, so let's see if we can actually make this algorithmic. So what does it mean that phi is of this format? So basically I should be able to write phi as some non-negative coefficient times this part plus some other non-negative coefficient times the second linear expression, and so on. So let's call these non-negative coefficients lambda. So what was phi? Phi was B0 plus, make sure you can see this. So B0 plus B1, V1, so on to ER, VR. And this should be equal to, well, some constant, let's call it lambda 1, times the first inequality here. So the left-hand side of the first inequality. So lambda 1 times A10 plus A11 V1, so on to A1 R VR, plus lambda 2 times the second inequality, A20, A21 V1, so on, A2R VR. And this goes on and on until we have lambda n times the last inequality, AN0 plus AN1, 1, so on to ANR. Okay, and also we wanted to have some multiple of this trivial inequality, so I'm going to just add some lambda 0 here. So lambda 0 plus lambda 1 times this, plus lambda 2 times this one, so on to lambda n times this. Okay. So if I am given a set phi, a set psi, and also an inequality phi, and if I want to see whether I can deduce phi from psi, now what I have to do is to just solve this. So, and by solving this, I mean that I have to find values for these multipliers, for lambda 0, lambda 1 to lambda n, right? Because everything else was given to me in the input. Okay, and note that this equality should hold for all values of the variables v1 to vr. Okay, so I have a linear inequality, and this linear inequality holds for all values of v1 to vr. What does that mean? That means that the corresponding coefficients should be equal on both sides. So on this side, I have b0, and on this side, I have lambda 0, right? What else do I have? I also have lambda 1, A10. I have lambda 2, A20, so on. So these are the coefficients of the units, and they should be equal on both sides. Then the multiplier of V1 should be equal on both sides. So B1 should be equal to lambda 1 times A11 plus lambda 2 times A21, so on, to lambda n times AN1. Okay, so let's actually write these down. So first of all, we know that B0, which is the constant coefficient on the left-hand side, should be equal to the constant on the right-hand side, which is lambda 0 plus sum of lambda I, AI 0. Right, and this is I from 1 to n. Okay, how about the other one? So B1, which is the coefficient of V1 on the left-hand side, should be equal to the coefficient of V1 on the right-hand side. And that's basically lambda 1 times A11, so on, to lambda n times AN1, which is sum of I from 1 to n, lambda I, A, I1, right? And generally, we can write this for every B. So I can basically say that every Bj should basically be sum of I from 1 to n, lambda I, Aij. Right? Hopefully, I didn't make any mistakes with the indices there. So Now, something magical has happened here, actually. And the magical thing that has happened is that we started with this. This entailment. And this was a set of inequalities over a bunch of variables, V1 to VR. This was another inequality over these variables. Then we rewrote this using Farkas lemma and got this equality. And if you look here, you see that the variables are still there. So I have V1 to VR still here. But then I could translate this and just say that the coefficients on both sides should be equal. And I got a bunch of equalities. And in these equalities, I don't have any of my original variables. I don't have V1 to VR in these new equalities that I have here, right? So basically, what this means is that I got rid of this whole quantification over all the possible values of V1 to VR. And this basically means that all I have to do at this point is just to solve these equalities, right? And of course, I also have the constraints that all of our lambda i's are greater than or equal to 0, because we could only multiply our inequalities by non-negative values. So what is this? This is basically a linear programming instance. I can give this to an LP solver, and it will solve it for me in polynomial time. So that's the magic of Farkas lemma. You start with really complicated constraints of this form. These are entailments that should hold for all values of your program variables. But then in the end, what you get is just simply a linear programming instance. And now this is what we're going to use for solving our, for synthesizing our ranking function, okay? So let's go back to our program. And let's write some of the conditions for the ranking function. Well, actually, we did this in the previous session, so I'm not going to write all of them. Let's just write some of them. So we said that the ranking function should be non-negative. So if I want to write the non-negativity, let's say at line 2, this means that for every value of x, if the invariant at line 2 holds, then I should have f2 be greater than or equal to 0, right? And if I write this in a more concrete way, this is basically for all values of x. Now, what is invariant at point 2? It's that x is between 1 and 10, on x 10. Then what should I have? I should have c2x plus c3 is greater than or equal to 0, right? And actually, I can still rewrite this so that it becomes in this. I just want to massage it into this nice format that we had here, that a bunch of things are non-negative. So x is less than or equal to 10, so 10 minus x is greater than or equal to 0. And also x minus 1 is greater than or equal to 0. And this should entail that c2x bar plus c3 is greater than or equal to 0. Right? Okay. Now, we apply Farkas lemma. And by applying Farkas lemma, it means that we should be able to write this right-hand side as a combination of the left-hand side and also the trivial inequality. So I should have for all x bar, c2x bar plus c3 is some non-negative constant plus some coefficient times 10 minus x bar plus some other coefficient times x bar minus 1. Right? Okay. Now I want to get rid of the quantification over x bar. So I just say that the constants on both sides should be equal, and also the multiple or the coefficient of x bar on both sides should be equal. So the constants. On the left-hand side, we have C3. On the right-hand side, we have lambda 0. We have 10 lambda 1. And we have minus lambda 2. Right? Okay. And now the coefficient of x. On the left-hand side, we have C2. On the right-hand side, we have minus lambda 1 plus lambda 2. Okay. So now all we have to do is that we have to solve these inequalities. And also we know that we should have lambda 0, lambda 1, and lambda 2 greater than or equal to 0. Okay. So this constraint was rewritten equivalently as this linear programming instance. Now I should do the same thing for all of my constraints. So let me just do it for another constraint. So let's do it for a constraint that has epsilon in it. For example, if you consider the transition from line 1 to line 2. Okay. What happens? Well, we have the invariant I1 at line 1, and we also know that x was greater than or equal to 0, otherwise we wouldn't go to line 2. And from this, we want to deduce that the value of f decreases by at least epsilon. Right? So let me try another paper. Okay, so this is what I have. I have for every x, if it satisfies the invariant at line 1, and also it's greater than or equal to 1, because that's the while condition. Then when I go to line 2, my value is f2 of x, right? And this should be less than or equal to f1 minus some epsilon. Okay, let's expand this. So this is for every x bar. I1 says that x is between 0 and 10, and this says x is greater than or equal to 1. So x is between 1 and 10. So I can just write x minus 1 greater than 0 and 10 minus x greater than 0. So this part is the same as before. Now we just have to figure out this part. So this is basically f1 minus f2 minus epsilon is greater than or equal to 0. And I can again rewrite that. So this is the same thing that we had before. Okay, what is f1 minus f2 minus epsilon? So this is f1 and this is f2. We can easily compute that. This is c0 x bar plus c1 minus c2 x bar minus c3 minus epsilon greater than. Okay. Now, again, we apply Farquhar lemma, so we have to write the right-hand side as a combination of the left-hand side. So we have to say that C0 x bar plus C1 minus C2 x bar minus C3 minus epsilon is equal to some constant plus some constant times x bar minus 1 plus some other constant times 10 minus x1. Okay, and now again, we get rid of the quantifier there by just saying that the corresponding coefficients should be equal on both sides. So what is the constant factor here? We have C1 on the left-hand side minus C3 minus epsilon. And this should be equal to lambda 0 minus lambda 1 plus 10 lambda 2. Okay, maybe I shouldn't call them lambda anymore because I already used lambda there. So let's call this lambda prime. Okay. And I have to also say that the coefficient of x is equal on both sides, on the left-hand side and the right-hand side. So the coefficient of x on the left-hand side is C0 minus C2. And on the right-hand side, it's lambda 1 prime, lambda 1 prime minus lambda 2 prime. Okay. Now, and of course, I also should have lambda 1 prime greater than or equal to 0, and lambda 2 prime greater than or equal to 0, and also lambda 0 prime. Okay, so basically, I do this for all of my constraints, for all of my non-negativity constraints, and also for all of my ranking constraints that basically at every transition, the value of the ranking function should decrease. And for each one of them, I get a bunch of equivalent, I get a linear programming equivalent instance, a bunch of equivalent linear programming constraints. And then I should just put all of these together. So I write down everything that I had for that constraint, everything that I have for this constraint, and every other constraint. I just put them together. I get a huge linear programming instance. And I just have to solve that huge linear programming instance. And that linear programming instance gives me values for the lambdas and also for epsilon and the c's. Oh, and I should also have epsilon greater than 0. We need that one to be the definition of a ranking function. So yeah, basically, this is the way we can automate the whole process. So instead of guessing the coefficients, we can just turn the whole problem of synthesizing a ranking function into linear programming and then just give that to an LP solver, and it will give you values for all of your coefficients if they exist. Okay, now remember that in the previous session, we talked about 3 important properties when we were talking about termination. And we said that termination being undecidable means that we cannot have an algorithm that has all 3 properties. And the 3 properties were soundness, completeness, and termination. Okay. But now we actually have an algorithm for proving halting, right? We have an algorithm for synthesizing these kind of linear ranking functions. So the question is, which one of these properties do we have? Is our algorithm sound? Any ideas? Well, what does soundness mean? Soundness means that if the algorithm succeeds in proving termination, then the proof is actually correct and the program really does terminate. So if our algorithm succeeds, if our LP solver succeeds and gives us some values for our coefficients, then of course we get a ranking function, and that ranking function proves termination for our program. So we definitely have soundness. Do we have termination? Well, all of the things that we did can be done in polynomial time. So we get a linear programming instance which has polynomial size. And it's very well known that linear programming can be solved in polynomial time. So not only we have termination for our verification algorithm, we actually even have a polynomial runtime. So this one also holds. But what about completeness? So do we have completeness here? Well, of course, we don't have completeness, because if we had it, then the halting problem would not be undecidable. So what does it mean that we don't have completeness? What it means is that sometimes our algorithm would fail and would say, okay, I couldn't find any ranking function. For example, we create our linear programming instance, we give the linear programming instance to an LP solver, and the LP solver says, okay, this instance has no answer. When that happens, we are not sure if the program actually terminates or not. Why? Because the only thing that we know is that we don't have a linear ranking function. We don't know if we can have ranking functions of other types or not. So we don't have completeness, but we actually have something that is kind of better than nothing. We have completeness for linear ranking functions. So we have completeness in the sense that if a linear ranking function exists, then our algorithm would find it. And why do we have that? Because, well, every step of the algorithm was basically based on a theorem that gave us equivalent constraints, right? We started with constraints that were the definition of the ranking function, and at every step we just changed their format, but we kept them equivalent. So that was the whole point of Farkas lemma. The whole point of Farkas lemma is that it says this constraint holds if and only if we can write phi as a non-negative combination and so on. And because this is if and only if, so we're not losing completeness there. So we have completeness for linear ranking functions. In other words, we actually have a sound, complete, and terminating algorithm, but it's not really an algorithm that decides termination. It's an algorithm that decides the special case of termination. It decides whether your program has a linear ranking function or not. Okay. Now, is this any good? Why would we need such a thing in the real world? So basically the question is, if I have some program in the real world, how likely is it that it has a linear ranking function? And if my program somehow didn't have a linear ranking function, then how likely is it that it actually terminates? It's actually not hard to think of programs that do not have linear ranking functions, right? So a very simple example of this would be just two while loops. So let's say that I have I1, J1. So basically two while loops that just count from 1 to n. So if I have or two for loops that are just nested and count from 1 to n, why wouldn't I have a linear ranking function for this program? Well, because if you go back to the whole concept of ranking function and how we prove the existence of ranking function, basically the ranking function gives you an upper bound on the number of steps that you should still take until you get to termination, right? And here the number of steps that you should take is quadratic. So you can't really have a linear ranking function here. Okay. So what else can we do? We have an algorithm that can prove termination in some specific cases, in the case of existence of linear ranking functions, but we also have much more general programs. And we want to be able to prove termination for these more general programs. Now, the idea that is often used for these kinds of problems is what we call modularity. Or sometimes it's also called, let's see, that was another name for it. Yeah, I forgot the other name. Okay, so the idea that is often used here is called modularity, and it's very simple. So let's say that you have a block of code. This block is X. Okay. And let's say that you know that this block of code always terminates. Right. So what happens if you take X and plug it into some other code? So what happens if you have some while loop, and then inside that while loop, you have X? Would this program also terminate? Well, not necessarily, right? Because, for example, this can just be while true and just do X over and over again. But if I know that X terminates, and if I know that Y also terminates, then I would be able to deduce that if I put them together right after each other, then this will also terminate, right? Oh, okay. I remembered the other word. The other word is compositionality. This is the same as majority. Okay. So basically, I can have some sort of a termination rule. I can say that, let's say, term X means that X terminates. So what I can do is that I can say if X terminates and Y terminates, then XY will also terminate. Right. So how does this help? The way it helps is that if you are given a big program, instead of having to find a linear ranking function for the whole program, you can first find it for some part of it. Terminates. Okay. You can first find a linear ranking function for the first part, for example, for X. And then you can find another linear ranking function for the second part. So this is the termination rule for composition, for sequential composition. And what happens if I have something else? So what happens if I have a program that is of this form? So if some condition G, then do X, else do Y. Okay. Again, the situation is kind of similar. Instead of finding a ranking function, a linear ranking function for the whole thing, what I can do is that I can find a linear ranking function for X, showing that X terminates, and find a linear ranking function for Y, showing that Y terminates. And this would be enough to prove that the whole thing terminates, right? Because when I evaluate this condition G, and either it holds, in which case I go to X, or it doesn't hold, in which case I go to Y. But there's actually a little bit more that we can do here. So if this G holds, then I know that at the beginning of X, I have G, right? So I can kind of use G as an invariant at the first line of X, and then find a linear ranking function for this program, for the program X that has G as an invariant in its first line. And I can do the same thing for Y. So let me just misuse the notation a little bit and write it like this, term of Gx. And what I mean by this is that I'm assuming G as an invariant at the first line of X. And if I have term of also not G, Y, then I can be sure that this whole thing terminates. Okay. So again, instead of finding a linear ranking function for the whole program, I just need to find a linear ranking function for X, and I also get some bonus assumptions that help me in finding that linear ranking function. And then I have to find similarly a linear ranking function for Y. Now, the part that is actually kind of hard is the rule for Y, right? It's always like that. So what happens if I have while g x? So we want to write something similar, but it's not that easy, right? Okay, so what we want to do is that we want to make sure that while g, maybe let me add 2 and alt, 2x alt terminates. Okay. So the first thing that I need is that I want every iteration of the while loop to terminate, right? Because if I don't have termination for every iteration, then I don't have termination overall. So I can say that, so at every iteration, I am starting to run x, and I also have the assumption g at the first line of x as an invariant. So this is again term of gx. Okay, so I definitely need this. But what this assumption tells me right now is that every iteration of my while loop will terminate. It doesn't really tell me what happens with the while loop itself. So the while loop might run forever. Okay. So what we need here is something that is called a loop variant, or sometimes a loop ranking function. So it's very similar to a normal ranking function. So in a normal ranking function, we assigned some value to every state of the program, and we said that, okay, at every step of execution, I want my value to decrease, but I also want to be sure that the value is bounded from below and it can't decrease forever, right? So I do something very similar here, but instead of giving a value to every state of the program, I just give a value to the beginning of every iteration, the states that are at the beginning of every iteration. So I find some expression or some function such that the value of this function is bounded from below, and also it decreases by at least epsilon in every iteration. Okay, so let's call that function f. So what do I want to have? Of course, I want to have f always greater than or equal to 0. But I also want the value of f to decrease in every iteration. So what does that mean? So if the value of f is some value, let's call it v, and g holds, then I run one iteration of my while loop. And at the end of this, the value of f should be less than v, or less than v minus epsilon, based on which kind of ranking function it is. Okay. So this is a little bit more complicated than the previous rules that we had. So if we have a program like this and we want to prove its termination, we first find the ranking function for x itself, assuming g at the beginning of x. And after we did that, we should also do some meta ranking function synthesis. Basically, we have to synthesize this f, which is kind of also like a ranking function. So its value is always greater than or equal to 0. And its value decreases every time you run the entirety of x. But you can synthesize this f exactly in the same way that you synthesize a ranking function, right? It's the same problem. So if we assume linearity in all of this, then this can also be solved by Farkas-Lemma. So why is this whole thing useful? Because now if I have an example like this, what I have to do is that first I prove this terminates, then I prove this while terminates, then I prove the inside of this other while terminates, then I prove that the whole of this other while terminates. So I have this kind of modular reasoning where I start from the innermost loop and just prove termination and come out. And I at least have a sound and complete algorithm for finding linear ranking functions at every step. So in the end, what happens is that I can actually prove termination for a lot of programs that do not have linear ranking functions, as long as every step here in this system, has some sort of linear ranking function or linear loop variant. Okay, so this is how we do termination analysis. Any questions until this point? Okay, great. So now finally, let's talk about what this paper does. So all of this was the background of the paper. And now we're going to talk about what the contribution of this paper was that we were supposed to read. So let me share the paper with you. And let me just talk over this paper. So just a second. Okay. So first of all, what this paper does is that it looks into loops of a very special form. And the special form of loop that it looks into is this. So it looks into loops where the constraint of the loop is a bunch of linear inequalities. And also inside the loop, we have some sort of non-deterministic assignment. And the only rule is that our non-deterministic assignment should satisfy a bunch of linear inequalities. So X is the value of the variables before this iteration of the loop, and X prime is the value of the variables after the current iteration of the loop. And basically the only thing that we know about the loop body is this. So a bunch of constraints on the previous values and the new values, and these constraints are also linear. Okay. So actually this is very similar to our own while language in a way, but it has kind of a more expressive non-determinism in it, right? Because if your value is X before you run one iteration of the loop, then at the end, your value can be any X prime as long as it satisfies these constraints. So the value of X prime is not really defined uniquely based on X, and it can have infinitely many possibilities for even one given X. Okay, so it looks into whiles of this form, but honestly, when I was reading this paper, I think that they didn't have to limit themselves to this kind of while loops. They could basically handle much more general cases as well. Okay. Now, what is the problem? The problem is, as usual, proving termination. So we have a while loop of this form, and we want to prove that every possible run of this while loop terminates. And of course, they're just focusing on a single while loop because that's the hardest thing to solve. Everything else could kind of be handled by the modularity. So what's the point here? So the point is that originally you would just find a linear ranking function using Farkas lemma. But if you have a linear ranking function, that means that you should have a function whose value always decreases, right? But there are many cases where you cannot find such functions. Let me see if I can find an example of this somewhere here. Okay, eventual linear ranking functions. Oh, okay, so they have actually an example of a loop where this doesn't happen. Well, the example is not very illustrative, so okay. Anyway, just take me at my word that there are many cases where you have loops, and these loops don't actually have a normal ranking function. You can't find a function that always decreases. So the very simple and basic idea behind this paper is that it's fine if we allow our function to increase for a while, as long as we are sure that after a finite increase, it will start decreasing. Okay, and this is what they call an eventual ranking function. So in other words, let me see. Okay, so an eventual ranking function for a loop is basically a map. And you see, the thing that we have here is that we have some function f, and also we have some other function rho. So instead of just having one ranking function, we have two different functions now. And the condition that we want to satisfy is that if the value of f is greater than some k, and if we transition from x to x prime, then the value of rho should decrease. Okay, so instead of one function, we have two functions. We have f and we have rho. We start running our loop, and initially we don't care about rho at all. Right? We just work with f. And we only care about rho when the value of f gets greater than or equal to some threshold. Okay? And we are also assuming that f is an increasing function. So f of x is a linear increasing function. So what does this mean? This means that I'm running my loop, and at the beginning, what I'm doing is that I have this function f, and in every iteration, I'm just increasing the value of f. But at some point, the value of f would get greater than or equal to k. And when that happens, then from that point onwards, the other function rho is a ranking function. And it proves the termination of the loop. Now, why does this work? Quite simply, you have two cases. The first case is if you just keep running your loop and the value of f keeps increasing, right? So if it keeps increasing forever, at some point its value would get greater than or equal to k, because we are working in, let's say, natural numbers. And when its value becomes greater than or equal to k, then you suddenly have a ranking function rho. So as long as you're sure that at some point the value of f gets to k, you are sure that you will get your ranking function and your loop terminates. But what's the bad case? The bad case is, of course, if the value of f does not increase enough to get to this threshold k. But f itself is an increasing function. So if the value of f increases in every iteration and it never gets to k, so you have less than k iterations overall and you're terminating. So in both cases, having this kind of f and rho proves termination. So that's the basic idea behind this paper. And now the only difference with synthesizing normal ranking functions is that here you have two different functions. You have f and you have rho. And you have to define templates for each one of them. And also you have kind of a fancier constraint. But again, as you see, the constraint is of a form that you can apply Farkas lemma. So the constraint just says that for every possible valuation, if some linear inequalities hold, then some other linear inequalities should also hold. So you can definitely just apply Farkas lemma here as well. It's a bit more complicated than normal ranking functions, but all of these steps are the same. And in the end, you will get a polynomial size LP instance, and you can solve it in polynomial time. So this is the whole point of this paper. Okay. Now I'm going to talk a little bit about some other techniques that we use when we don't have linear ranking functions. So this paper was one of them. So you can use two functions, and this is what they call an eventual ranking function. But there are some other ideas that are prominent as well. So let me just switch to the visualizer and give you some other ideas. And no matter how you define your ranking function, whether you use normal ranking function, eventual ranking function, or any of these ideas that I'm going to present now, in the end, you get a bunch of constraints and you can apply Farkas-Lemma. So the synthesis algorithm is always the same. Okay. So the first thing that I want to talk about is what we call a lexicographic ranking function. Okay. And the idea here is that, again, recall from the last session that S is the set of reachable states in our program. And previously we had a function F that mapped every state in S to, let's say, a natural number. Right? And it also had other constraints on it. So it decreased at every step of execution. So that was good. But now in a lexicographic ranking function, the idea is that instead of mapping it to a single natural number, let's map it to k different natural numbers. So let's map it to a vector of k numbers. Okay. But we should also have some sort of decrease condition. So the way that we do that is that we say if some state S prime is a successor of another state S, and f of S prime is, let's say, I don't know, A1, A2, A prime 1, A prime 2 to A prime k. And let's say f of S is A1, A2 to AK. Okay. So each one of these states is mapped to k natural numbers. And this one, S prime, is a successor of this one, S. So what I want to have is that I want the vector assigned to S prime to be lexicographically less than the vector assigned to S. And by lexicographically, I mean, like, think of it as a dictionary order. So we first compare the first components. And if one of them is less, then that vector is overall less than the other one. If the first components are equal, we compare the second component and so on. Okay. So this is the concept of lexicographic ranking function. And of course, you can find linear lexicographic ranking functions, again, using Farkas-Lemma. It's very similar to ranking functions. The only difference is that you have more constraints. But why does this work? So why does the program terminate if and only if it has a lexicographic ranking function? Well, if a program terminates, then it has a ranking function, and a ranking function is a special case of a lexicographic ranking function. So this side is trivial. On the other hand, if your program has a lexicographic ranking function, then why does it have to terminate? Because, well, it starts with f of S0, right? And f of S0 is a vector of k natural numbers. And there are finitely many other vectors that are lexicographically less than or equal to this, right? So you cannot take infinitely many steps. So a lexicographic ranking function also proves termination. Next. But another thing that is actually quite interesting, and this is the part where my own research is currently doing, is what happens if we look into more complicated ranking functions, especially what happens if we have polynomial ranking functions. So in linear ranking functions, if your program variables were, let's say, x and y. Then at line 1 of your program, you would say that my function is what? It's like C0 plus C1x plus C2y. Right. And then you would find values for C0, C1, and C2. But what happens if we look at polynomial ranking functions? So let's say that I want, for example, a quadratic ranking function. So I want f1 of xy to be C0, C1x, C2y, C3 x squared, C4xy, C5y squared. Okay. What happens if I have these kinds of constraints, these kinds of ranking functions? Okay, the thing that happens is that we can do the exact same thing that we did before with the linear case. So we can first write these constraints that should hold in order for f to be a ranking function. But the difference is that before we had constraints that were linear on both sides. So it was that we had a bunch of linear inequalities, and they should lead to a linear, some other linear inequality. They should basically imply another linear inequality. But the implication right now is a little bit different. So on this side, we are still linear, right? Because we assume that our invariants and programs are linear. But on the other side, we have polynomials. Okay. So we cannot apply Farkas lemma. And the reason is this, well, in Farkas lemma, what we had was a condition for having some linear inequality phi be implied by a set of linear inequalities. But now our phi is polynomial. So we kind of need, let's say, an extension or a generalization of Farkas lemma in this case. And I'm going to show you one example of this kind of generalization. So it's called Handelman's theorem. Let me see, I should have it in my own paper. So let me share this screen with you. Okay, this is what we call Handelman's theorem. And so Handelman's theorem is basically an extension of Farkas lemma when the inequality that you want on the right-hand side is polynomial instead of linear. So the idea is this. Let's say that we have a set of variables. So V is V1 to VR. And let's say that this is the set of our assumptions. So we have a bunch of linear inequalities, and this means that it's either greater than or equal to or just greater than. So it's some sort of comparison here. So we have a bunch of linear inequalities, but then from these linear inequalities, we want to deduce some polynomial inequality. So let's look into what kind of polynomial inequalities we can get out of our linear inequalities. Okay. So first of all, we define the notion of monoid. So the monoid of a set of linear inequalities is basically any polynomial that can be obtained by multiplying the left-hand side of some of these inequalities. Right? So if I know that this thing is greater than or equal to 0, and if I know that this thing is also greater than or equal to 0, I can multiply them, and the result is also non-negative. It's greater than or equal to 0. Right? So this is the basic idea behind the monoid. So the monoid of a set of linear expressions is basically the set of all polynomials that can be obtained by multiplying these linear expressions together. Okay? Now, this is the theorem of Handelman. The theorem of Handelman says that if you have a bunch of linear inequalities and some other constraints, which I will come back to, then these linear inequalities lead to some polynomial g being greater than 0. Basically, these inequalities imply that polynomial g is greater than 0, if and only if g can be written as a non-negative combination of all the polynomials that are in the monoid. So the idea is simple. If we had a bunch of linear expressions that were non-negative, we know that we can multiply them together and we will still get non-negative polynomials, right? These were called the monoid. Now, we have a bunch of non-negative polynomials in our monoid. We can get linear non-negative combinations of these, and those will also be non-negative, right? So as long as I can write G as a linear combination of HIs, and each HI is in my monoid, then G is non-negative. And what Handelman does is that it's kind of also proving the other side. Of course, it comes with some side conditions. And basically, it proves that if phi implies that G is positive, and if phi is satisfiable, and if the set of points that satisfy phi is compact, and so on, then the opposite of what I said also holds. So then G can definitely be written in this form. So even without these conditions, we know that if we can write G in this form, then G is non-negative. But what the theorem says is that if these conditions hold, then any non-negative, any positive G can be written in this form. Okay. So this is the way that we can actually extend Farkas lemma to the polynomial case, and we will probably see more of this. But how does this lead to linear programming? The way it leads to linear programming for our cases is that, well, the G here is our F, so it's the ranking function that had to be non-negative, right? And our ranking function is a polynomial of a certain degree. So let's say that if I wanted to find a quadratic ranking function, then I know that this polynomial G here is of degree 2, right? So a polynomial of degree 2, if I want to write it as a linear combination of other polynomials, I'm sure that all of these other polynomials are also of degree at most 2. Right? Because if I have a degree 3 polynomial here, not exactly. Well, yes, okay. Because this, no, that doesn't work, sorry. No, the yi's are positive, but the leading coefficient in the polynomial can be negative. Okay, yeah. But so yes, we can't just assume that the HIs have a bounded degree, but what we can do in practice is that we can say, okay, instead of just looking at the entire monoid, which is most likely an infinite set because it's the set of all polynomials that are somehow obtained by multiplying these linear inequalities. What we can do is that we can say, okay, we look only into the elements of monoid up to a certain degree. And this kind of loses completeness, but not so much. right? So basically the way that it works is that I say, okay, let's first try with monoid bounded by degree 2. If I found a solution, that's great. If I didn't find a solution, I just increase my degree and try again. Okay. And if I do this, then I will either get a solution if it exists, or I will run forever. So there is always this kind of trade-off between completeness and termination and so on. But these kinds of things are called actually semi-complete algorithms. And the idea in a semi-complete algorithm is that you have some parameter, let's call it k, for example, in this case, the maximum degree that we have in our monoid. And the thing that you can prove is that your algorithm is sound, complete, and terminating if this parameter is chosen to be large enough. Right? So if you choose a large enough bound for the degree of the polynomials in your monoid, you will be able to get a sound and complete and terminating algorithm. But choosing that bound is theoretically a very hard problem, but in practice, it's really an easy problem. It usually works with 4 or 5. So that's the way that we can handle polynomial ranking functions. But what's even more interesting is what happens if here, instead of having a bunch of linear inequalities, we have a bunch of polynomial inequalities. So what happens if not only the right-hand side is polynomial, but also our assumptions are polynomial? So this corresponds to the case where your program has polynomial assignments or polynomial invariants or maybe polynomial guards for the while loops. And that's actually also solvable. But that gets into real algebraic geometry. And it's way above the level of this class for now. So all I want you to know is how we use Farkash lemma to synthesize linear ranking functions, linear eventual ranking functions, and linear lexicographic ranking functions. But I also want you to be aware that there are ways of doing this for the polynomial case as well, even though they're much harder. But eventually, what happens is that in practice, most of the time we just use the linear ranking functions or linear eventual or lexicographic ranking functions, and then just use these rules of compositionality to prove termination for general programs. And honestly, the current state of affairs is not very nice. So we can most of the time kind of prove termination for the programs that we care about. But of course, the problem is undecidable. So in many cases, we just either get lucky or rewrite the program so that we get lucky. But what's really important is that if you are writing a safety critical program, for example, if you're writing a program that controls, I don't know, let's say a medical equipment or some airplane autopilot or something that handles millions of dollars in money, then you should be able to prove these kind of things. You should be able to prove termination, you should be able to prove safety. And if you can't, and if the algorithms are not good enough to prove the property that you want, you just have to rewrite the program over and over again until you have the proof. And this is quite hard for software engineers, but that's the only way we have, because for safety critical programs, we should have proofs that the program is correct. Okay, any questions? Okay, so let me stop the recording first.